Hello and welcome. I hope this lecture finds you well. We're going to chat a little bit about our approximate analysis method for our course ENG 8411 Structural Analysis. First of all, I want to acknowledge that the reason that this lecture has been posted online is because of the latest development related to the state of emergency called by the province of Ontario, and as a result also by Algonquin College. And this is as a result of COVID-19. However, I want you and me to recognize that we'll do fine. And by that I don't mean that this is not a serious matter, rather that you, my students, and I, your professor, are going to work together to make the best of it. That way your education will not be interrupted unnecessarily and we can still get through the content of this course. You and I will make it work. Patience will be the name of the game. So the story so far, basically, where we are at this point. So far, we've been working with statically determinate structures, and by that I mean basically structures that use equilibrium only. And that's easy peasy, right? Usually we just use our three equations of equilibrium and we just rock the heck out of it. So for example, for a beam like the one you see here, notice how at the very left end it has a fixed support. Along its span L, it has any type of load. Well, the reactions are as shown, three reactions. We have three equations of equilibrium, and therefore we can find those reactions no problem. Okay? So the idea behind static equilibrium is that we have as many equations of equilibrium as we do reactions. Well, the problem comes when we have so-called structurally indeterminate structures. And by that I mean structures for which the number of reactions is greater than the number of equilibrium equations at our disposal. Specifically, let's assume you have a beam like this, very similar to the previous one. However, a hinge has now been added as a support on the right-hand side. Well, notice how now the number of reactions is 5. However, we still only have three equations of equilibrium. That means we're missing two equations of equilibrium to solve for all 5 unknowns. How do we do it? Well, the idea is that we're going to be able to do it, and we're going to use one approach, at least for this topic. And this approach we'll identify as the approximate method. The idea behind the approximate method is as follows. Are you ready for it? Because I'm sure that you're going to go, You basically find hidden hinges, and then bam, once you find these hidden hinges, you can solve the question, right? Remember how we used hinges previously to solve questions that appear to be indeterminate. We'll do the same thing here. I need to caution you though, this does take some experience, and that translates to practice, practice, practice. That's where your homework comes into play. You want to make sure basically that you're ready to be able to solve any kind of question that I may throw your way. So let's look at example number 1. We did this together in class, and I want to point out that the one we did in class had a difference. The support at B was not a hinge, rather it was a roller. Well, we solved this out, and remember how I had to build a model for it to actually measure out where the hinge was, where this inflection point was. Very well. The idea behind this method of approximate analysis is that we have to find the location of this hidden hinge. The fancy word for this hidden hinge is inflection point. Okay? And inflection points, the locations of them, follow a very specific set of rules for this method. They are as follows. These are the 3 different rules we're going to follow. Now, I've copied and pasted these from your course notes. They're exactly the same ones we covered in class. And they had to do with the end of a beam, it had to do with intermediate supports, and it had to do with a fixed support. Well, here's something that I want to point out to you. Did you notice this YouTube icon that appeared? I want you to download your course notes for topic 5 again. They have now been modified. So download the PDF document for topic 5, you will notice that when you get to these rules on the course notes, there is an icon here on the PDF, and you can actually click on it. That icon will take you to a video that I've created for you that explains these rules. Or in general terms, whenever you find that icon in our course notes, it means that will link you to a video. If you find more than one icon like this, that means more than one video has been linked. That way, you have an opportunity to go online, view these videos at your leisure, at your speed. You can pause, rewind, fast forward, and I think you'll do fine. So in general terms, this too is present in your course notes. I use this image in your course notes to illustrate exactly in images, by actually doing it, what those 3 rules mean. This too is linked to a YouTube video, so check it out, okay? Moving on, this here is example number 2. We did it in class. This example as well in your course notes, so make sure you download them. Now has a YouTube link. So download this PDF document and you can click on this YouTube link in your course notes. We then did example 3 in class for this one, and it too has a link to a YouTube solution. And I want to remind you that this question was also covered previously when we did shear and bending moment diagrams. Do you remember that? Do you remember why I chatted a little bit about this question? It's because of what happens when the shape of a structure's bending moment diagram matches the shape of the structure. This here is a bridge that used to exist in Los Angeles, and we chatted a bit about it when we covered this question, and its shape matches the shape of the bending moment diagram for that structure. When that is the case, then the structure either acts in tension or compression or both. There is very little bending in the structure itself. Okay, moving on to example 4. We did this in class again, and it's kind of like a revisited version of example 1. And a reminder here that at B, this is actually supposed to be a roller. As you can see, the YouTube link has appeared. That means in your course notes, there is a clickable link to a YouTube video. At this point, we're ready to move on to frames. So we've worked on beams so far. Let's move on to frames and using this approximate method for frames. Here is an example of a frame, example 5. I've linked for you, as you can see, another series of YouTube videos to give you the solution on how to analyze this kind of structure. Frames are important to view because the interesting thing about them is that they're corners. These corners right here, they act as intermediate supports. So check out the solution for this, which I've posted for you, and you'll be able to solve it no problem. Lastly, example 6. I don't post a solution for this. I leave it for you to do as homework, practice. But maybe I want to talk a little bit about it. For this beam, there is a fixed support at A and roller supports at B, C, and D. That means a total of 6 reactions. We only have 3 equations of equilibrium. That means we have to come up with 3 more equations to solve for those unknowns. That means we are going to have to split this structure at least 3 more times to come up with those equilibrium equations, which means that we have to find at least 3 locations of inflection points. Here's a tip. There's going to be one here, and one here. Okay? I want to conclude this topic by letting you know that homework is posted for you. Notice, or remember what I mentioned, that is that practice is what's going to help you for this. Well, I posted extra examples for you to do as homework. One of them, I believe it's example 11, also has a link to a YouTube explanation for it. I wish you the best, and I know you're going to do well. if you have any questions, please make sure to email me. It's important that you take the time to review the videos that I've linked for you, and if you have any questions on them, let me know, and maybe we'll schedule some type of video chat to discuss it further. Thank you for your time, and I wish you good luck.